Hey folks, how's it going? So, a previous video there, I did a video where I showed a live stream of a flat earther called Gene Techman, and he was talking about the vacuum catastrophe, which has to do with a massive difference in the quantum field theory predictions of the vacuum force density, the vacuum density force, as opposed to what is observed and measured in cosmology. And he actually responded to my videos. And I'll put those up here in just a second here. And I'm going to show you, he actually did a video as well. And then he actually, funny enough, and he can't seem to realize this. He showed his own AI from ChatGPT. And his AI from ChatGPT, his whole entire video, proved my point and disproved his point. And he's too thick to have realized it. And I've pointed this out to him, I don't know how many times. And he keeps talking about Richard Feynman and what did he say? And I've told him this about 5, 6, 7, 10 times what Richard Feynman said and what he meant about the teacup. And what he doesn't realize is what Feynman was saying, word for word, is that if the vacuum force density had the amount of energy that is calculated, predicted by quantum field theory, then a teacup worth would be enough to vaporize all the oceans. But it doesn't have that much energy, because the observations and measurements show that there's a massive discrepancy between the prediction and the observation. And that is what the vacuum force density is. It's the discrepancy between what we see and what we measure. And something that Gene Techman cannot seem to comprehend this very simple and observable and demonstrable reality and fact. So see what he has to say, and then we'll go from there. And he's been in my comments a lot. I mean, I'm living rent free in this guy's head right now. It's quite funny. Alright, so here's some of the comments he's done on my video. Also, you can see that he's posted a response video to this. And there's actually more comments he's done. He just keeps going and going. I'm definitely living rent-free in this guy's head. And he keeps asking the same question. I keep getting the same answers, and he asks the same question again, hoping to get a different answer, and he keeps getting the same answers. He doesn't like them. Okay, so I'm going to put the part of the video he actually put me in his video. The rest of his video I actually include because he puts like snippets, because he's cherry-picked some stuff from some videos that discusses this. I put the whole entire videos on. I didn't put the physicist Akaku in, because he's just kind of, the whole point, he's just saying a physicist said something, and I put up stuff from physics that say the same thing. So it doesn't really matter. His physicist, one physicist, his Akaku is the same thing I did, which is that the calculations in quantum field theory and predictions don't match the observations and measurements we have, and that is what the vacuum catastrophe is all about. Is the fact is that the predictions in our math isn't explaining what we're seeing in reality and the phenomenon that we measure and observe. Something that Gene just doesn't quite seem to understand is that the vacuum of space doesn't hold 10 to 120th power energy. That's not what is observed, but that's what the quantum field theory calculation predictions show. So there's something in our predictions and our maths that aren't adding up. I've explained this several times, but Gene Techman either refuses or is too stupid to recognize what the issue is. I think he's just cherry picking this, hoping that people won't look into it. And now he's freaking out because somebody has looked into it and is exposing his lies. Just have a look at the video he's put up, and then I'm going to show you part of his video. He ends up debunking himself using AI, and it's rather funny, so have a look, and I'll read it up to you when it gets up for it. Come across Ricky is live. He's a flat earther, and they're going on, and he had Gene Techman on there, who's a narcissistic, freaking egotistical jerk, and he's been called up many times. And he thinks he's quite clever, and the more you watch him and look up all his crap he says, the more you realize he's just a dumbass, like all flat earthers. And he happened to bring up this thing called the vacuum catastrophe. He thinks somehow this disproves the global model and heliocentric model. That was funny because, honestly, full disclosure, I didn't know what this was. I never heard of this, so I looked it up. And Gene technically needs to look it up too, because what he cites is completely wrong, right? Now, it comes down to it, he thinks if you had a teacup size of a vacuum, like a space, which is a nearly perfect vacuum, but not the perfect vacuum, it would cause... Now, Gene claims that what I had put up in my previous video where I discussed it with AI, where like, so how questions are leading AI or weren't. I actually did very open questions and let AI just give honest answers. Now what he's done is he's done the whole thing where he's tried to lead AI with in ChatGPT, but try to specify things and play word games. So it's often done by flat earthers. Let's have a look. Okay, so Gene asks, did Richard Feynman claim that one teacup of space would make all of the oceans boil as it relates to the vacuum catastrophe? Response is, yes, Richard Feynman is often cited in discussions about field catastrophe. Refers to the enormous discrepancy between the quantum field theory's predicted vacuum energy density and the observed value from cosmology. So already there, the first sentence in response proves exactly what I was saying, in which the predictions done in quantum field theory do not match the observations in cosmology. Observations what actually is happening, and quantum field theory predictions are what our mathematics and our understanding of physics and how what they predict. So what is all it's saying is that we don't understand certain parts of what's happening. Doesn't mean it proves that it's happening, because, well, no, we know what proves it's happening. In quantum field theory, we're not able to make the predictions and understand all the mechanisms of what's observed and measured. And this is what Gene, where the loss is, where he doesn't understand this. Continuing on, the theoretical calculations suggest that the energy density of the vacuum should be around 120 times larger than what we observe, making it one of the biggest unsolved problems in physics. Note that I said theoretical calculations and not absolute observations. Now, if you note in this one here, ChatGPT actually had some points he made below, and Gene decided to cut off all of point 1 and most of point 2. Why he do that? Because it probably debunked everything he was saying and falsified what he had to say. This is flat Earth at its best, but a lie to Flerf. Cause all the oceans on the planet to boil instantly, like just go straight from liquid water straight to gas, no questions asked. So the top part there says estimated at 10 to the 26 joules. If the quantum vacuum energy density were correct, even a small amount of space, like a teacup, would hold much more energy than this, making it powerful enough to vaporize all of water on Earth. And point 3 says the cosmological constant problem. However, astronomical observations, such as those related to dark energy and the expansion of the universe, suggest that the vacuum energy is much, much smaller than QFT predicts. So the massive discrepancy between theory and observation is what is the vacuum density energy and why it's so big. Oh dear, Gene. I don't think you quite understand exactly what you've put up. How did I explain this to you? Quantum theory, field theory, what you're referring to is calculations that are based on predictions. See, there are predictions that are not fitting with reality. See, they've done cosmology measurements. Now, I know you have a hard time with measurements because flat earthers don't like the new measurements because they tend to kind of falsify the flat earth. But what is the whole thing of your vacuum catastrophe thing, where the disconnect is, you're not getting this, is really funny, and even one of your videos kind of debunks you, and I'm going to show you the full video, not the cherry pick part you did. It says that what we observe does not match what the mathematical predictions show. So what that's really saying is that our understanding of physics and our predictions that we make with the math is not quite working right now, and we need to learn more. So what we predict is not working with what we observe, but what we observe works. Now, all this has nothing to do with the heliocentric globe model. You see, the vacuum catastrophe and the fundamentals of how the vacuum of space works doesn't affect the fact the globe is still reality, and the heliocentric model and the globe heliocentric model is all backed up by mountains upon mountains of evidence that don't need quantum field theory and don't need the vacuum catastrophe. But let's just look at your video that you put up, and then let's look at a few more videos that, well, shows the math. I know you don't like the math. The best thing you always throw out is your 8 inches per mile squared, and you use it wrong. I'm sorry. You don't measure curvature by inches because its curvature has to do with like changes of angles. So you use degrees, because that's how curvature is measured. You don't measure curves in inches, you measure it in degrees. Degrees of curvature. Say it slowly for you. I know it's hard. Degrees is measured, curvature is measured in degrees. Degrees. If you get a protractor out and you look, it uses degrees, not inches. Learn the proper formula. But let's move on and let's completely destroy your vacuum catastrophe. I already have, but why not? Let's do it again since you decided to tag me into something. Well, I thought I'd return a courtesy.
The most successful theory in all of physics is arguably quantum field theory. It's made the most precise predictions in all of science, but it's also made the worst. There's a massive disagreement between the theoretical and the measured values of the energy of the vacuum. We call this theoretical fail the vacuum catastrophe. The quantum vacuum is a seething ocean of activity. Virtual particles appear and vanish from nowhere in seeming violation of our intuitions about the conservation of mass and energy. We saw in our recent episode that we can thank the Heisenberg uncertainty principle for this bizarre behavior. It tells us that there's a quantum fuzziness in the amount of energy contained at every point in space, a non-zero, zero-point energy in the quantum fields that can briefly manifest as particles. This suggests that space itself contains energy. But how much energy? Quantum field theory predicts that the energy of the vacuum should be up to 120 orders of magnitude greater than the measured value.
Oh, so it's the prediction doesn't match the measurements. So we have measurements, but the predictions that we have aren't quite working. So we can measure it, we can observe it, observations, and we can measure it, but the math of how to math it out isn't quite working. But we have observations and measurements, but we can't do the predictions yet. Okay, so we can measure it and observe it, but we still need to work on how to predict it accurately. I don't see the problem here yet, other than we need to work on the math. But it still doesn't prove the flat Earth.
It's one of the greatest unsolved problems in physics. Let's talk about vacuum energy from a theoretical standpoint. From the perspective of quantum field theory, every point in space is represented by a quantum oscillator, one for each elementary particle type. Higher energy oscillations represent the presence of real particles. However, even the lowest possible energy oscillation, the one corresponding to the absence of particles, the so-called vacuum state, has some energy. To satisfy the Heisenberg uncertainty principle, the vacuum state of any field oscillation must be half of the tiny Planck constant times the frequency of that oscillation. Now, that's a minuscule amount of energy. Except, to properly describe a perfect vacuum, every single possible frequency mode at every point in space must have that amount of energy. To calculate the density of energy of the vacuum, we should add this tiny energy over an infinite range of frequency modes for all fields. Now, multiply a finite energy density, no matter how small, by infinity, and you get infinite energy density. We'll get back to whether the idea of infinite vacuum energy is actually possible. It certainly sounds a bit excessive, so maybe we can avoid it. Let's think in terms of the electromagnetic field. What if there's a maximum possible frequency for virtual photons? Then our sum of frequency modes would be finite. Now, it sounds like a hack, and it sort of is, but we're getting desperate. And anyway, there's an almost sensible cutoff for photon frequency. It's where photon energy is equal to the Planck energy, or 10 to the power of 19 giga-electron volts. This is where our understanding of physics breaks down. Until we develop a theory of quantum gravity, we can't say whether photons above this energy are possible. So, if we add up the vacuum energy, including virtual photons, all the way up to the Planck energy, we get a finite number. A very, very large finite number. The energy density would be 10 to the power of 112 ergs per centimeter cubed. This back-of-the-envelope estimate was first made by John Wheeler and Richard Feynman, who noted that one...
Oh, so it was a back-of-the-envelope estimate using quantum field theory and making a prediction, and then with the limited knowledge they had in, what was it, 1970s or 80s, that Feynman was actually doing research and stuff like that, or the 1960s? It was 1960s. I'm pretty sure we've actually advanced a lot further than then, since, well, didn't Feynman die in 1988? If I'm not mistaken, I'm pretty sure quantum field theory, we have a lot more other science and mathematics and advancements in science since 1988. So, yes, let's have a quick look and see the advancements we've had in physics and quantum physics since Richard Feynman's passing in 1988. He died from cancer. Let's see. Has science and technology advanced since 1988? Gee, I wonder. Let's have a look. Let's start with advancements in physics. So here we are from 1987, so just before Feynman passed away, and we're moving on, and all this stuff, we're in the 20th century, it's the 21st century. Oh wow, look at all this. We seem to have advanced quite a bit since 1988, in which Richard Feynman may have actually made his propositions and did his mathematics in quantum field theory. Wow. So Gene Techman is relying on somebody who died in 1988 and had knowledge from before the 1980s. Well, let's look at quantum physics. Holy crap. Wow, look at all this. There seems to be quite a lot of advancements and stuff that Feynman would have never known about. Like the Bose-Huygens particle that was discovered in CERN. That's one of them. Look at that. Let's see. 21st century. Because we're in the 21st century now. No longer do we live in the 1980s. We have a lot of advancements in technology, and science just keeps expanding, and our knowledge keeps growing. We may not have solved the vacuum catastrophe yet, but we're much closer than when Feynman is around, that's for sure. So, so his predictions by the math that he done in the back of the envelope don't work, reflect what we can see in reality. So we need to get our understanding better and get some better math. Okay, still doesn't disprove the globe.
A teacup of space with this energy density would contain enough energy to boil all of the oceans on the planet. Yet, even if vacuum energy did have a value this high, in fact, even if it were infinite...
Oh, so he said, if the energy density was that high, or if it is infinite, then they have enough energy. If the predictions were true, which we know they're not true because our measurements and observations show that it doesn't have energy density of 10 to the power of 124. So what he's saying, that if it was like that, but it isn't that dense, it doesn't have that much energy because observations and measurements prove it doesn't have that, and we need to work on our understanding, get better, and figure out why our observations and measurements show it's much, much less by a degree of 124, 10 to 124 zeros. We need to get better at doing the math or figure out what mechanics or what is working that is doing that. So the math isn't working because we need to understand better, but observations and measurements show that the math doesn't work, and so the observations don't work. So that teacup thing is a what if based on theoretical mathematics predictions that don't work. Okay, still doesn't disprove the globe.
We may not notice, at least according to quantum theory, In fact, in both quantum mechanics and classical mechanics, a particle's equations of motion depend only on changes in energy. The 0 point of the energy scale is irrelevant. As long as the vacuum energy is the same everywhere, then it's inaccessible to us as an energy source. We're going to come back to that point in an upcoming episode, so you'll be able to knowledgeably scoff at 0 point energy perpetual motion machines. Long story short, a crazily high, even infinite vacuum energy doesn't affect the predictions of quantum field theory. Just redefine the 0 point to whatever you want, and you're good to go. However, you can't be so cavalier with general relativity. Einstein's theory tells us that any form of energy produces gravity, and what matters is the absolute amount of energy, not relative deviations. Vacuum energy should produce a gravitational effect, and a huge vacuum energy should produce a huge gravitational effect.
Oh, so vacuum field energy needs gravity. Hold on, Gene, I don't think you believe in gravity. But what you're citing here requires gravity. So, because you use special relativity, which uses gravity, and vacuum energy requires gravity, and a massive amount of gravity. Vacuum energy requires a lot of gravity. Hold on, wait a minute, Gene. Your videos just debunked you because you don't believe in vacuums in gravity. So you can't use vacuum energy because vacuum energy says that gravity exists, and you don't believe in gravity, so you don't believe in this. So your citation just debunked your belief that you think that gravity doesn't exist, that you think it's electromagnetism or density or buoyancy or whatever other crap you're making up that makes absolutely no sense. But what you're stating here is gravity. You don't believe in gravity. So, thanks. You believe in gravity now. So you believe in gravity. Welcome to the globe. Thanks for playing.
That effect would be seen in two ways. An energy of space itself should cause exponential expansion, at least in the case of an already expanding universe. It should also massively increase the spatial curvature of the universe. Now, this is all extremely unintuitive, and we spent 5 episodes trying to give you a sense of why this is true. Now, feel free to jump down that rabbit hole if you haven't already, but the upshot is that if vacuum energy really did have the enormous value predicted by theory, then our gently expanding, geometrically flat universe would not exist. The realization of this fact in the early days of quantum field theory was the beginning of what would become the vacuum catastrophe. But it wasn't a full-blown catastrophe yet. There was still a way out. If some fields can have extremely large positive 0 point energies, then perhaps others have extremely large negative 0 point energies that cancel them out. An extension to the standard model of particle physics called supersymmetry may partially allow this. It gives all particles a supersymmetric counterpart that may precisely cancel out their vacuum energy. Now, basic supersymmetry only allows us to cancel out photons down to the so-called electroweak energy, which brings the predicted vacuum energy down to a mere 10 to the 47 ergs per centimeter cubed. But perhaps a yet deeper theory allows perfect cancelling down to 0. For a while, theorists assumed that something like this must be happening, meaning the vacuum energy was really 0. It was a glimmer of hope that catastrophe could be averted. That is, until we discovered dark energy. In the late 90s...
Hold on, wait a minute. Did you say you discovered dark energy late 90s? Or 90s? When did Feynman die? Yeah, so you're citing somebody who doesn't even know our current cosmology or astrophysics or quantum physics. So you're using old information, and we have new information. Good job, Gene. You keep freaking cherry picking on old stuff. I'm going to rely on the new stuff.
Astronomers discovered that the expansion of the universe is, in fact, accelerating in exactly the way we'd expect from a non-zero vacuum energy. Now, unlike the Lamb shift or the Casimir effect, the observation of accelerating expansion allows us to measure the absolute density of vacuum energy. Assuming vacuum energy is to blame, dark energy weighs in at 10 to the power of negative 8 ergs per centimeter cubed. Compare that to the number predicted by quantum field theory. There's a discrepancy of 120 orders of magnitude between the two, or 55 orders of magnitude if we use the electroweak energy cutoff instead of the Planck energy cutoff. Now that is what scientists call a catastrophe. QFT can give us an extremely high vacuum energy, or a vacuum energy of exactly 0 if we assume symmetry of positive and negative 0 points between different fields. But a very small, non-zero vacuum energy? That requires what we call fine-tuning. Gigantic positive and gigantic negative 0 point energies would need to cancel each other out down to a very tiny non-zero value. That sounds like a ridiculously unlikely bit of luck if we can't invoke symmetries. A proposed solution is the anthropic one. We exist in an extremely rare universe whose fundamental fields cancelled out their 0 point energies, or at least enough of them to allow life and astronomers to evolve. That would imply countless other universes with different, less comfortable vacuum energies. Of course, it may be that advances in theory will resolve this catastrophe without requiring us to invoke the anthropic principle. In the meantime, the conundrum continues to perplex physicists and will do so until we reach a deeper understanding of the true nature of space-time.
But like I said before, I'll say it now, Gene, you don't seem to still understand this. Because as I said, and I'll say it again, you're basing it on quantum field theories, hypothesis, predictions, which is mathematics, which are not working up to what is observed and measured in cosmology. So yes, okay, there is a massive discrepancy, and discrepancy lies in our understanding of the physics. We can see it, we can measure it, we're just not quite at the point now where we can explain exactly what's going on, and so can't make predictions of it, but we can see it and measure it. And it still has nothing to do with the heliocentric globe model, because that's a completely different thing, which is seen, measured, and proven through countless experiments, observations, calculations, and everything else. Meanwhile, the flat Earth, well, it can't even predict sunrise, sunsets, or you can't even use a flat Earth to predict the eclipse that's happening tonight on March 14th.
Imagine a cubic region of space with side lengths equal to the Planck length, then the volume of this region of space will be equal to the Planck length cubed. So we're now finally in a position to estimate the energy density of empty space due to the quantum vacuum fluctuations. We simply need to divide the Planck energy by the Planck volume, and we find that this is equal to the speed of light raised to the power of 7 divided by g squared times h bar. If we substitute the numerical values for these constants, then we find that the predicted energy density of the vacuum is approximately 10 to the power of 114 joules per meter cubed, which is an incredibly large density. Just to put this in perspective, this energy has a mass equivalent of around 10 to the 97 kilograms per meter cubed, which really is beyond comprehension. This is equivalent to squeezing the mass of a billion trillion Andromeda galaxies into 1 cubic meter.
Which is why our calculations and our understandings of the physics of the universe need to get better, and because obviously the math ain't mathing now, is it? And it's not matching up to what we're seeing and measuring in cosmology and in reality. This is something that Gene just can't seem to quite comprehend, or he refuses to. But I'm starting to think he's just not smart enough to quite understand it and grasp it. So I'm hoping that some of this will somehow sink into that six head it's got going on there.
And all of this energy is predicted to exist as a result of quantum fluctuations arising from our most successful theory of fundamental physics. So how does this predicted value compare with the observed vacuum energy density? And for that matter, how do experimental cosmologists measure the energy density of the vacuum? To answer these questions, let us momentarily return to the Friedmann equation. Now, if you recall, we can rewrite this expression so that every term inside the bracket has units of energy density. We see that there are three major contributions to the energy density. There is the density due to the matter content of the universe. There is the vacuum energy density due to dark energy, which we've just been discussing. And then there is the term which we can loosely interpret as the energy density due to the curvature of space. One of the big challenges in experimental cosmology is to measure the values of these three contributions to the overall energy density of the universe. So how is this done? Well, over the past few decades, several different techniques have been used to measure and constrain the possible values of these energy density parameters. In particular, observations of the luminosities of Type 1a supernova, along with the measurements of the small irregularities in the cosmic microwave background radiation, place tight constraints on the measured values of the energy densities.
All right, so like real observations that we actually have done, and measurements we've taken, and not just predictions using math and our limited understanding of the physics of the vacuum of the universe. Oh, and so we kind of can see what's going on and understand it. At least to that point, we can observe what's going on.
Now, it's conventional to express the measured energy densities in terms of the critical density that we calculated earlier. If you recall, the critical density represented the important threshold separating an open and closed universe. Now, according to the most up-to-date experimental data, the energy density due to the matter content of the universe is measured to be roughly 30% of the critical density, whereas the energy density due to the curvature of space is measured to be very close to zero. In other words, it appears as if the universe is spatially flat and that the curvature kappa that we encountered earlier is zero. Finally, the measured acceleration rate of the universe suggests that the energy density due to dark energy is around 70% of the critical density. And so we see that if we add together all of the contributions, the total energy density of the universe is in fact remarkably close to the critical density. And so it appears that we live in a finely balanced, spatially flat universe.
All right, that finely balanced, spatially flat universe, that would be impossible if the vacuum energy was 10 to 125 orders greater than what we observed. Oh, so then what we observe and measure contradicts that. And so everything Gene is saying is bullshit. Okay.
It's also worth mentioning that detailed measurements of the rotation rates of galaxies suggest that visible matter only accounts for roughly 4% of the energy content of the universe, whereas around 26% of the content is due to the presence of dark matter. As the name suggests, dark matter is the name that physicists give to matter that doesn't interact with light, and hence we cannot see it. We can only infer its existence from its gravitational effect. A detailed discussion of dark matter will no doubt form the basis of a future video, but for now the important point to focus on is that the energy density of our universe is totally dominated by dark matter and dark energy, whereas the visible matter contained in all of the stars and galaxies and in you and I only accounts for a tiny fraction of the energy density of the universe. So how does the measured value of the dark energy density compare with the theoretical value that we calculated earlier? Well, if you recall, the predicted theoretical value was a staggering 10 to the power of 114 joules per meter cubed, whereas we've just seen that the measured value is roughly 70% of the critical energy density, which is around 10 to the minus 10 joules per meter cubed.
All right, so like I said before, the predicted calculated value, so the prediction doesn't match the observation. So something's going wrong here. And since the measurements and observations we can see and we can measure, then the most likely it is down to the math and the predictions that we seem to be getting wrong, and that we need to expand our knowledge more on that side and figure out what it is that we're seeing and how can we predict it and how can we explain and calculate it. So certain parts missing. Still not falsifying the globe, still not falsifying the heliocentric model. The only thing that's showing so far, and Gene can't understand this, is that there are some gaps in our knowledge when it comes to the physics of the vacuum of space. That's all it is.
And so we see that the predicted value is 10 to the power of 124 times greater than the measured value. This is without a doubt the worst mismatch between prediction and observation in the history of physics.
Did you get that? Mismatch between observation and prediction. That's all it is.
And it is this mismatch that forms the basis of one of the great unsolved problems in fundamental physics, the so-called cosmological constant problem, also known as the vacuum catastrophe. So why is this problem labelled a catastrophe? To see why, let's take a look at what would happen to our universe if the predicted value of the energy density was indeed correct. In that case, we see from the energy density relationship that we encountered earlier that a large vacuum energy density corresponds to a large cosmological constant. So what does a large cosmological constant imply? Well, if we go back to the Friedmann equation, then we see from the right-hand side of this expression that if the cosmological constant term is very large, it will dominate the other terms on the right-hand side. And so in this case, we can neglect the other two terms and write the Friedmann equation as a dot over a squared equals lambda over 3. And if we then rewrite the cosmological constant in terms of the vacuum energy density, we find the following green expression. Next, we can rewrite the left-hand side in terms of the Hubble parameter h, and then square root both sides in order to obtain an expression for the Hubble parameter in terms of the vacuum energy density. Next, because the Hubble parameter is equal to a dot over a, we can rearrange this and write a dot equals ha, which is simply telling us that the rate of change of the scale factor a is proportional to the scale factor. In mathematics, when the rate of change of a quantity is proportional to the quantity itself, this indicates exponential growth. And so we can solve this equation for a and write this as a of t equals a naught e to the ht, where a of naught is the scale factor at the present moment when t equals 0. You can check that this is indeed a solution to the scale factor equation by substituting it back into the green differential equation. So what is this yellow exponential equation telling us? This is saying that in a universe dominated by dark energy, the growth in the size of the universe will be exponential, with the rate of exponential growth determined by the Hubble parameter, which in turn is determined by the energy density contribution of the vacuum. So what happens if we substitute the predicted value of the vacuum energy density that we calculated earlier into this equation? To be precise, let's use the predicted value of the vacuum energy density to predict how long it will take for the universe to double in size. In other words, we want to find the time taken for a to equal 2 times a naught. To do this, we simply need to substitute this constraint into the exponential growth equation. And if we do this, we find that 2a naught equals a naught e to the ht. If we then cancel a naught from both sides, and then take the natural logarithm of both sides, and then rearrange for t, we arrive at the expression t equals log of 2 over h. This equation will provide an estimate of the time taken for the universe to double in size. All we need to do is substitute the predicted value of the vacuum energy density into this equation. And if we do this, we find that the predicted value of t is around 10 to the minus 43 seconds. And so we see we've come full circle, and that our predicted value of the vacuum energy density implies that the universe should be doubling in size every 10 to the minus 43 seconds, and consequently, everything within it should be ripped apart in the next millionth of a trillionth of a trillionth of a trillionth of a second. But this is clearly not happening. In fact, when we use the experimentally determined value of the vacuum energy density, we find that the universe is in fact doubling in size roughly every 10 billion years. This is yet another way of dramatically emphasizing how big a problem the vacuum energy catastrophe is.
Yes, the problem is that the math and predictions that we're using and the math that we have in understanding isn't representing what we are measuring and what we are observing. That's the problem. Nothing to do with what Gene is talking about, because Gene doesn't understand any of this whatsoever. It's gone way over his head about, I'd say, about 25 minutes ago in this video.
So what do physicists do? Well, there is actually one very simple way to solve the problem. Since we know that the observed value of the cosmological constant is of order 10 to the power 124 times smaller than the calculated quantum vacuum contribution, one approach is to say that this quantum value is essentially a correction to an already existing classical value. In other words, we simply assert that the measured value of the cosmological constant is the difference between a classical and quantum contribution. According to this approach, if the calculated quantum cosmological constant has some numerical value, for example 4.66145 ... then the classical contribution to the cosmological constant must be minus 4.66145 ... 516. In other words, the classical contribution would have to cancel the quantum contribution to 124 decimal places in order for the remainder to be equal to the measured value. In principle, nothing stops us from simply asserting that this is the case. However, unsurprisingly, many physicists feel deeply uncomfortable with this approach, and as a result, this kind of quick fix solution is known as fine-tuning. This is a bit like walking into a room and finding a sharp pencil delicately balancing on its tip. Although this is physically possible, if you saw such a pencil, you would probably think that something was up, and you would seek an alternative explanation. For example, perhaps a fine thread is holding the pencil, or the pencil is actually glued to the table. You would be reluctant to immediately conclude that the pencil was perfectly balanced. And the same is true with the vacuum energy catastrophe. The fine-tuning solution just doesn't feel right. Some physicists have attempted to justify the fine-tuning argument by referring to the anthropic principle within the context of string theory. Without going into too much detail, according to string theory, the most fundamental constituents of nature consist of vibrating filaments of energy known as strings. Different vibrations of these fundamental strings correspond to different particles. The only problem is that string theory also predicts that there should be 6 extra dimensions of space that need to be curled up into a special type of geometrical shape known as a Calabi-Yau manifold. Unfortunately, there is more than one way of compactifying these extra dimensions. In fact, some conservative estimates put the number of ways of compactifying the dimensions at around 10 to the power 500. According to string theory, each possible compactification corresponds to a different vacuum state and therefore a different value of the cosmological constant. And so it is argued that in at least one such vacuum state, the fine-tuning cancellation will occur naturally. Leonard Susskind, amongst others, has argued that the existence of a large number of vacua puts anthropic reasoning on firm ground, since only those universes with properties conducive to the existence of human observers are ever observed, while a possibly much larger set of universes lacking such properties go unnoticed. Due to the central role that human existence plays in such an argument, this type of reasoning is referred to as anthropic reasoning. But understandably, many physicists are unhappy with this kind of explanation, especially within the context of a theory that has not been experimentally verified, which is still the case with string theory. And so I will resist the temptation to conjecture how the vacuum energy catastrophe will ultimately be solved. Rather, I will live in hope that someone watching this video may feel sufficiently inspired to tackle one of the most significant and long-lasting problems of fundamental physics. I think it only appropriate that I end with a quote from Einstein, who first conceived the idea of the cosmological constant. He said, "The search for truth is more precious than its possession." Long may the search continue.
The vacuum catastrophe is one of the biggest unsolved mysteries in theoretical physics. It highlights a shocking disagreement between quantum field theory and cosmological observations. According to quantum mechanics, empty space, the vacuum, is not actually empty. It is teeming with virtual particles constantly popping in and out of existence due to quantum fluctuations. These fluctuations contribute to the vacuum energy, which in turn should cause space itself to expand at a staggering rate. But here's the paradox. When physicists calculate the vacuum energy density from quantum field theory, the result is 120 orders of magnitude larger than what is observed in the real universe. In other words, the theoretical vacuum energy should be so enormous that the universe should have torn itself apart long ago. Yet, what we actually observe is a gentle cosmic expansion driven by dark energy, which seems to account for only a tiny fraction of this predicted vacuum energy. To put this mismatch into perspective, imagine you're measuring the weight of a feather, but your calculations suggest it should be as heavy as the entire Earth. That's how extreme the discrepancy is. How could our most successful theories predict something so wrong? Some researchers suggest that unknown cancellation mechanisms or symmetries in nature might suppress the vacuum energy to its observed level. Others propose that our universe might be one of many, and we just happen to live in one where the vacuum energy is low enough to allow galaxies, stars, and life to exist. This paradox has major implications. It challenges our understanding of quantum mechanics, general relativity, and even the nature of space-time itself. If we could solve it, we might uncover the missing link between quantum physics and gravity, leading to breakthroughs in cosmology, high-energy physics, and even quantum technologies. Could it be that our equations are missing a fundamental ingredient? Or does this point toward entirely new physics? Solving the vacuum catastrophe could be the key to unlocking the deepest mysteries of the universe. Quantum field theory predicts that empty space should have an enormous energy density due to vacuum fluctuations, yet cosmological observations suggest an energy density that is over 120 orders of magnitude smaller. This discrepancy, known as the vacuum catastrophe, challenges our understanding of quantum physics and general relativity. Resolving this paradox could lead to breakthroughs in fundamental physics and quantum gravity. If vacuum energy were as high as predicted, it would cause the universe to expand at an unimaginable rate, preventing the formation of galaxies and stars. It's like calculating that your phone battery should last for millions of years based on atomic energy levels, but in reality, it only lasts a day. Something fundamental is missing in the theory. Quantum mechanics predicts that even in a perfect vacuum, fluctuations in the quantum fields create a non-zero energy, often referred to as zero-point energy. While this energy is real and measurable in effects like the Casimir force, extracting it as a usable energy source remains speculative due to the unknown nature of vacuum stability. If harnessable, zero-point energy could revolutionize energy production and space travel. The Casimir effect demonstrates that two uncharged parallel plates in a vacuum experience an attractive force due to suppressed quantum fluctuations between them. It's like feeling pressure in an empty room because tiny, undetectable air currents are constantly pushing on you. Dark energy is thought to be responsible for the accelerating expansion of the universe, and some theories suggest it could be linked to vacuum energy. However, the measured vacuum energy is vastly different from the amount needed to explain dark energy, raising questions about the nature of the vacuum and the fundamental constants of physics. This discrepancy remains one of the biggest unsolved mysteries in cosmology. Observations of distant supernovae show that the universe's expansion is accelerating, implying the presence of dark energy with an unknown origin. It's like expecting the warmth of a small candle to heat an entire city. Either the energy source is miscalculated, or an unknown mechanism is amplifying its effects. The inflationary model of the Big Bang suggests that tiny quantum fluctuations in vacuum energy were amplified to create the large-scale structure of the universe. These fluctuations, though originating from seemingly nothing, could have seeded galaxies and cosmic structures. This implies that what we call empty space is actually a dynamic quantum environment capable of generating entire universes. The cosmic microwave background radiation exhibits quantum-imprinted fluctuations that align with inflationary predictions. It's like rolling dice and watching small, random numbers grow into entire mountains. Tiny fluctuations in vacuum energy shaped everything we see. The Casimir effect demonstrates that the quantum vacuum exerts real forces, proving that empty space is filled with fluctuating fields. This experiment involves placing two metal plates extremely close together, leading to an attractive force due to differential vacuum energy between and outside the plates. This result confirms that vacuum fluctuations are a measurable physical reality, even though their large-scale effects remain mysterious. Casimir forces have been experimentally verified at nanoscales and influence micro-electromechanical systems by causing tiny components to stick together. It's like feeling an invisible wind push two sheets of paper together, even though the air around them appears still. In quantum field theory, the vacuum is never truly empty, but constantly fluctuates with virtual particles that momentarily appear and annihilate. These virtual particles contribute to observable effects, like the Lamb shift and Hawking radiation. Their existence suggests that even empty space plays an active role in particle interactions and energy conservation. The Hawking radiation predicted for black holes arises from vacuum fluctuations near the event horizon, leading to the gradual evaporation of black holes. It's like borrowing money from a bank that immediately disappears after a few seconds, except the temporary debt still affects reality. Some theories suggest that our three-dimensional universe, including vacuum energy, may be a projection of information stored on a two-dimensional boundary. This holographic principle, inspired by black hole thermodynamics, could provide a new way to resolve the vacuum catastrophe by redefining how energy density is calculated. If true, it implies that reality as we experience it is fundamentally encoded on a lower dimensional structure. The entropy of a black hole is proportional to the surface area of its event horizon rather than its volume, hinting at a fundamental role for information storage in physics. It's like a high-definition hologram. The image looks fully three-dimensional, but all the information is encoded on a flat surface. The discrepancy between quantum predictions and observed vacuum energy might signal the need for new physics, such as modifications to gravity, additional dimensions, or exotic quantum fields. Some theories propose that vacuum energy cancels out due to unknown symmetries, while others suggest new particles that interact with the vacuum in a way that remains undetected. Discovering these effects could reshape our understanding of space-time and energy. Supersymmetry, SUSY, predicts that for every known particle, there is a heavier superpartner that could help cancel vacuum energy contributions. It's like an elaborate accounting error. Something in the fundamental equations is miscalculated, but we don't yet know where the mistake is. Experiments with ultra-sensitive detectors, such as vacuum birefringence tests and quantum optic setups, aim to probe the true nature of the vacuum. If the vacuum energy discrepancy is due to hidden physics, these experiments may reveal new forces, particles, or quantum gravity effects. The results could have profound implications for energy generation, cosmology, and fundamental physics. The PVLAS experiment investigates whether vacuum fluctuations interact with strong magnetic fields in ways that standard physics cannot explain. It's like trying to listen for whispers in a noisy room. Using more sensitive instruments might reveal hidden messages in the background hum of reality.
So in the end, as I've proven here, and I've shown Gene Techman once again, I have proven that you don't understand a single thing you've said when it comes to this topic. I highly suggest you just leave this alone and walk away. You've been thoroughly and absolutely debunked and crushed on this. Because what it is you're trying to take a theory, a theoretical calculation that we don't fully quite have got all the numbers and mechanisms yet, and trying to apply it to something that we are observing and seeing. And that's what the whole thing's all about. As I've said several times in the comments, as I said previously before. The vacuum catastrophe is a discrepancy in what we see and measure. I know you hate that word because it hurts you so many different ways. And what we have found for our mathematical predictions when it comes to quantum field theory. And what that comes down to is the fact there's certain things we're not quite understanding yet, because science is still evolving and we're still learning more things and new things. And so we're trying to find the answers, how we can have mathematical equations that we can make accurate predictions that represent what we are seeing and measuring. We have measurements and we have observations already. We know what's going on. We can see it. We can measure it. Now we're trying to figure out the mechanisms of how that happens and what's causing it and how to make predictions. That's the only thing that is the big, huge catastrophe that you are trying to claim. Your whole teacup on the Earth thing that would evaporate boil all the oceans is down to a number that is a theoretical prediction that doesn't work and isn't in reality. Like the flat Earth, it's a fantasy number based on misunderstandings compared to what we actually see and observe. That's it. Bye-bye. See you later. You've been done. Poor sad Gene. He thinks he's so smart, and yet he's just Dunning-Kruger. Yes. The good stuff. Always sweeten my coffee with the tears of Flerfs.